Hello everyone, today we will learn about limit points and closure of sets and some theorems in metric space. Limit points. Let X be a metric space and A is a subset of X. A point X belongs to X is called a limit point or accumulation point or cluster point of the set A if each open sphere centered on X contains at least one limit point of A other than X. In other words, if open sphere SXR minus singleton set X intersection A is equal to non-empty. The set of all limit points of A denoted by A dash is called the derived set of A. Closure of a set. Let Xd be a metric space and A is a subset of X. The closure of A denoted by A bar is the union of A and the set of all its limit points A dash, that is A bar is equal to A union A dash. Some examples. Let RU be the usual metric space and A is subset of R. If A is closed interval AB, semi closed interval AB, semi open interval AB or open interval AB, then A dash is equal to closed interval AB. A is equal to 1, half, 1/3, then A dash, that is set of limit points or derived set of A, is singleton set 0. A is equal to Z or N, then A dash is equal to 5, because if we draw a sphere centered at 1, suppose this is S1 epsilon, then this open sphere does not have any elements of Z or N other than 1. Therefore, S1 epsilon intersection singleton set 1 is equal to empty. Therefore, 1 is not a limit point. Similarly, 2, 3, 4, etc. are not limit points of Z or N. Therefore, A dash is equal to empty. If A is equal to Q or set of rational numbers or set of irrational numbers Q complement or set of reals, then A dash is equal to R. Because if we draw a SXR, then every open sphere SXR contains at least one limit point of A other than X, that is SXR intersection singleton set S X is equal to non-empty. If A is equal to C, then A dash is equal to C. Means if A is equal to set of complex numbers, then its derived set is set of complex numbers. Now, closed sets. Let XD be a metric space and A is a subset of X. Then the set A is said to be closed if A contains all its limit points, that is, if A dash is contained in A. Examples: in the usual metric space RU, the set A is equal to 2, 3 is closed, since its derived set is equal to closed interval 2, 3, which is contained in A. If A is equal to semi-closed interval 2, 3, open at 2 and closed at 3, is not closed, since A dash is equal to closed interval 2, 3, which does not contain in A, because 2 does not belong to A. Therefore, A dash is equal to closed interval 2, 3, which is not contained in A. Therefore, A in this case not closed. If A is equal to Q or Q complement, that is rational numbers or irrational numbers, are not closed, since A dash is equal to R, which does not contain in Q or Q complement. A is equal to 1, half, 1/3, is not closed, since A dash is equal to singleton set 0, which does not contain in A, because A does not have element 0. Its limiting point is 0. Its limit point is only 0, which does not belong to A. Therefore, A dash is equal to 0, which does not contain in A. So, A is not closed. A is equal to R is closed, because A dash is equal to R. Now, theorem. Let XD be a metric space and F is a subset of X. Then F is closed if and only if its limit points F dash is contained in F. Proof. Suppose that F is closed. Necessary condition. Suppose that F is closed. We have to show that F dash is contained in F. That is, derived set is subset of F. If F dash is equal to empty, then F dash is equal to 5, which is contained in F. Therefore, our result is true. So, let F dash is non-empty and let X belongs to F dash. Then our aim is to show that X belongs to F. That is, we have to show that F dash is contained in F. If possible, suppose that X does not belong to F. Suppose X does not belong to F, then X must belong to its complement F complement C. This is the outer area of the boundary of F. Here X is the metric space, SXR is the open sphere. So, if possible, suppose that X does not belong to F, then X must belong to F complement. Suppose X belongs to its complement. Consequently, F dash is an open set containing X. Because we assume that F is closed, so its complement FC is an open set containing X. So, there exists an open sphere SXR containing F complement. So, this is point x outside of closed set F, which belongs to F complement. Since F complement is open, so there must exist an open sphere SXR, which is contained in F complement. That is, SXR contains no point of F. Here SXR is fully contained in F complement, and since F and F complement are disjoint, therefore SXR contains no point of F. This shows that X is not a limit point of F, that is, X does not belong to F dash, which is a contradiction to our assumption that X belongs to F dash. Therefore, our assumption is wrong, hence X belongs to F dash X belongs to F dash implies that X belongs to F, hence F dash is contained in F. Conversely, suppose that F dash is contained in F, we have to show that F is closed, or equivalently, we have to show that F complement is open. If F complement is empty, then it is open. So, let F complement is non-empty, and let F complement is non-empty and let X belongs to F complement. Then X does not belongs to F. Here X belongs to F complement, so F and F complement are disjoint, so X does not belong to F, and therefore X does not belong to F dash, as F dash is contained in F. Thus, X is neither a point of F nor a limit point of F. So, there exists an open sphere SXR disjoint from X, that is SXR fully contained in F complement. This shows that each point of F complement is the center of an open sphere contained in F complement. Therefore, F complement is open, hence F is closed. Theorem: let X be a metric space and A is contained in X, then A is closed if and only closure of A is equal to A. Proof: suppose that A is closed, we have to show that closure of A is equal to A. Since A is closed, if and only if A dash is contained in A by previous theorem, and closure of A is equal to A union A dash. So, closure of A is equal to A, as A dash is contained in A, therefore A union A dash is equal to A. So, closure of A is equal to A. Conversely, suppose that closure of A is equal to A, we have to show that A is closed. But closure of A is closed, so closure of A is equal to A, so closure of A is closed, therefore A is closed. Let S be a set of bounded sequences of the form x is equal to xi. If d s cross s to r defined by d of xy is equal to sigma I is equal to 1 to infinite 1 by 2 raised to the power I modulus xi minus I by 1 plus xi minus yi. Prove that SD is a metric space. Proof: let S be the set of bounded sequences of the form x is equal to xi of real numbers. For any two elements x is equal to x1, x2, xi and y is equal to y1, y2, yi of S, consider the mapping D from S cross S to R defined by d of xy is equal to this. we have to show that SD is a metric space. For this, we have to prove the four properties of a metric. We can easily verify that for any pair of elements x is equal to x1, x2, xi and y is equal to y1, y2, yi of S, d of xy is greater than or equal to 0 because this is positive quantity. So, dxy is greater than or equal to 0 for all x, y. Similarly, we can show that dxy is equal to 0 if and only if x is equal to y, because if this is equal to 0, then this quantity individually 0 and this modulus xi minus y is equal to 0, which implies that xi is equal to yi and implies that x is equal to y, and also dxy is equal to d of yx, because dxy is equal to this. If we take minus common from this, then it becomes modulus yi minus xy by 1 plus modulus yi minus xy, which gives d of yx. Therefore, d of xy is equal to d of yx. Now, in order to prove the triangle inequality, let z is equal to z1, z2, zi dot belongs to S. Then d of xy is equal to sigma I is equal to 1 to infinite 1 by 2 raised to the power I modulus xi minus yi by 1 plus modulus xi minus yi is equal to sigma I is equal to 1 to infinite 1 by 2 raised to the power I. Here we have z subtracted and zi subtracted and zi added. Therefore, there is no difference in the expression. So, this is equal to sigma I is equal to 1 to infinite 1 by 2 raised to the power I modulus xi minus zi plus zi minus yi by 1 plus xi minus zi plus zi minus yi modulus, which is less than or equal to sigma I is equal to 1 to infinite 1 by 2 raised to the power I modulus xi minus zi by 1 plus modulus xi minus zi plus sigma I is equal to 1 to infinite 1 by 2 raised to the power I modulus zi minus y by 1 plus modulus zi minus y. As this property holds, modulus alpha plus beta by 1 plus modulus alpha plus beta is less than or equal to modulus alpha by 1 plus modulus alpha plus modulus beta by 1 plus modulus beta. Now, this quantity is equal to d of xz and this quantity is equal to d of zy. Therefore, d of xy is less than or equal to dxz plus dzy. Hence, D is a metric on S and SD is a metric space. Thank you very much for watching this video.